Okay, so we're going to pick up, whoops. We're going to pick up right where we left off on Monday, talking about Markov chains. I won't rerun through all the definitions and things, but I will remind you of the fundamental theorem. Every irreducible finite aperiodic Markov chain has a unique stationary distribution pi with all the pi I are positive, and the hitting time, the return time for a particular state is just 1 over its stationary probability. And the number of visits goes to t times pi I as t goes to infinity. Number of visits in time t. These are the technical conditions about not having separate connected component, not having a disconnected state space, and not having periodicity cycles that you have to return to a particular state at periodic intervals. And we started looking at applications of this in random walks on undirected graphs. And I argued that the stationary distribution pi for a particular vertex was just equal to the degree of the vertex divided by twice the number of edges. And that this also determined the time that how quickly you would return to a vertex if you started at the vertex, right? I'll point out something a little bit interesting, which is that this quantity, right, it's saying the time to get back to state I if you start at state I. So it's not assuming that you start in the stationary distribution, right? So the stationary distribution is the thing that you stay in all the time. But this is positing that you start at a known state I, so you're not in the stationary distribution. But nevertheless, there's this connection to the stationary distribution in terms of how quickly you return to that state I. Okay? And this is all very intuitive because basically if your probability of being in state I is pi I, then by sort of laws of large numbers, you're, over a very long time, the fraction of times that you are in state I is going to be about pi I times the duration, right? Which means that the space between those occurrences has to be 1 over pi I in order for you to end up with the proper number of occurrences, right? And this can be formalized through something that's known as renewal theory, but I'm not going to, okay? So we have this nice stationary distribution for undirected graphs, and we started talking about how this can be used to solve the connectivity problem, right? So the ST connectivity problem, right? We showed an algorithm due to Savage, which took order log squared n time. And the nice thing about this is that it works even for directed graphs. Okay. Sorry, order log n space. Right? But we are now applying the same ideas to undirected graphs, and we said that, right, since you have this stationary probability, this which is going to be at least 1 over 2m, whatever your degree is, right? So there's an inverse polynomial probability of being in a particular on a particular vertex. So intuitively, you figure you're going to get there within a polynomial amount of time, right? No matter where you start from. I know I haven't quite proven that yet, okay? And I need to do that. But if it only takes you a polynomial amount of time to get to a state in expectation on an undirected graph, then we can solve undirected connectivity in log n space, right? Because all we need to do is keep track of time and whatever vertex it is that we're actually on at the current time, right? So undirected random walk is going to let us solve the problem in order log n time randomized. Okay. And this is going to prove that undirected ST connectivity is in this complexity class known as RL, randomized log space. Right? Back in the beginning of the class, we talked about P, polynomial time. We talked about RP, randomized polynomial time, so on and so forth, right? There are also complexity classes for the space-bounded problems, right? And log space is an interesting complexity class. There are some things you can do in log space and a lot of things that you can't. And this random walk algorithm is the first that proves that you can solve undirected ST connectivity in randomized log space. Okay. Meanwhile, for directed ST connectivity, we've only Savage's algorithm only gives this log squared n bound. All right, so let's sort of finish filling in the pieces of the proof that we need here. So we only have, from the fundamental theorem, the time to return to the state you start from. But I'm interested in the time to get from one state U to another state V, right? I want to get from a start state to a destination state in order to solve the undirected ST connectivity problem, right? So I'm going to solve that in 2 steps. First of all, I'm going to give a lemma that for adjacent vertices, U and V, the sum of the hitting times in each direction, which is called the commute time, is at most 2m. Okay? And remember, the commute time, so that's the time to start at U, visit V, and then come back. So it's like your commute to work. Okay? And basically, if I can prove something about adjacent vertices, then I can prove things about arbitrary vertices by looking at paths through the graph, right? So what's the proof of this theorem? This proof is based on a different Markov chain, which is the edge traversal Markov chain. So this is a Markov chain that is derived from the vertex traversal Markov chain that we've been looking at, and it basically looks at the series of edges that you traverse. Okay, so I start on vertex U, I traverse UV, so that's the first edge of this edge Markov chain. Now I'm on vertex V, so my next edge step has to be an edge leaving V, right? And so if you're given the sequence of vertices, the sequence of edges can be derived from it, but you can also just talk about that sequence of edges as the Markov chain which you're focusing on. Okay. And what's interesting about this Markov chain is that it is what is known as a doubly stochastic Markov chain. So we know that sort of by the definition of Markov chains, right? For a given starting for a given starting state U, the sum over V of PUV is equal to 1 because you have a probability 1 of going somewhere. But what makes it doubly stochastic is that also the sum over U of PUV is equal to 1. Okay, so This says that the row sums of your transition matrix are 1. This says that the column sums are also 1. Okay? And this is not necessarily the case, right? You can have plenty of interesting transition matrices that are not doubly stochastic, right? But this basically says there is 1 unit of probability coming into each vertex, or sorry, into each edge, because we're looking at the edge chain, right? But there's a unit of probability coming into each state as well as leaving this state. And in your homework, you show that it's like a 1-line proof that such chains have a uniform distribution. All the states have the same probability in the stationary distribution. Okay? Yes? Well, I haven't written it down formally, but it's what arises from looking at the sequence of edges that happen when you're using the vertex Markov chain. You can define this in either case, on either kind of graph, but this statement only applies to the undirected case. Oh, sorry. No, it actually applies to the directed case as well, right? So the probability that you transition from edge UV to edge VW is just 1 over the, oh no, it's only for the undirected case. The out degree of V, right? This is a definition that works even for directed graphs, but this claim about double stochastic is for undirected graphs. Exactly, right? It's the same random walk, right? We go from a vertex to a neighbor to a neighbor to a neighbor. It's just that instead of spitting out the list of vertices, we spit out the list of edges that we traverse. Yes?
I guess if you had an undirected graph, then your edge UV, your next possible edges are all the outgoing edges of both U and V.
No, because there's a direction of transition, right? So what comes out in the Markov chain is also specifying a direction in which you traverse the edge. Okay, thanks for clearing that up. So is this clear? All right. So if it has a uniform distribution, then right we know pi sub e is equal to 1 over, it's 2m because there are 2 directions that you can be traversing the edge, right? So essentially we've turned the undirected graph into a directed graph with twice as many edges going in both directions, right? So the probability for an edge in a direction is 1 over 2m, which means that the return time for an edge is just equal to 2m, right? So this essentially proves the claim of the lemma, because suppose that you arrive at V using edge UV. Okay. Well, what that means is that in expected time 2m, we will use UV again. Right? So essentially, but if we do that, if we use UV again, that means that we sort of traversed from U to V, and then we got back to U in order to use UV again. Yes? So I'm not making, sorry, that's a temporary assumption. Let me sort of clear it up, right? So the point here is that, again, in terms of the Markov chain over time, there's going to be this traversal of UV, and then some stuff is going to happen. And then after expected 2m time, we're going to traverse UV again, right? So every 2m steps or so, we're going to see another occurrence of traversal from U to V, right? So if we start pretty much anywhere in this, sorry, so this is true if we arrive, sorry, I'm tangling myself up. Because we have these spaced out every 2m steps, you're going to have a complete commute from U back to V every 2m steps. And so it doesn't really matter where you start counting, right? The commute time, right? You're going to have this return after 2m steps. And so it's going to give you a total time of UV in expectation, okay? Okay, so this tells us about that it doesn't take too long to get from a vertex to its neighbor, okay? And by bootstrapping off of that, we can now talk about getting anywhere, right? So what is the expected time to get from an arbitrary U to a V? Well, it's at most the time, the sum of the commute times on a path. Right? So it's at most the distance times 2m. Right? We can also observe that the cover time, the time to visit all of the vertices in the graph, is the expected time to commute on all the edges of a spanning tree. In DFS order. So that's at most 2m times n. Okay. And so this gives us, I mean, this is what we need for testing ST connectivity, right? Is that the commute time for S to T is at most 2mn, even if they're n steps apart. And this gives us the stronger result about visiting all of the vertices of the graph. Okay? So that kind of ends the story for ST connectivity in randomized log space. There's actually been a lot of progress since then. First of all, there is primarily, Reingold et al. Showed that undirected ST connectivity is in log space. They de-randomized this walk algorithm. And it uses a lot of sophisticated ideas from expanders, which I've mentioned before. And it essentially, you can essentially show that on expanders, and I'll talk about this a little bit later in the lecture, you get places very quickly. You very quickly end up in a uniform distribution on the place you are in the vertex. And they give an interesting construction called the zigzag graph product that kind of in place transforms your graph into an expanderish kind of graph, so that the time that it takes to get to another vertex drops dramatically and yields this deterministic bound. Still open is whether directed ST connectivity is in log space. ST connectivity is complete for randomized log space, just like NP completeness. And so in fact, if you show that directed ST connectivity is in log space, this would imply that randomization does not help in log space. It would show that every problem, yes? Sorry, for NL, thank you. And that would show that non-deterministic log space and randomized log space are contained in log space, okay? We also have, but what we do have, another sort of de-randomization trick is that it is in order log to the 3/2 of n space. So there have been improvements on Savage's algorithm, which was log squared, to log to the 3/2. And this uses some clever pseudorandom generator tricks. That they developed a pseudorandom generator that can fool space-bounded algorithms so that you can de-randomize using that pseudorandom generator. Okay. Okay. I want to go a little farther, though, before we abandon undirected graph walks, because there's another sort of fun idea that you get from these random walks, which is universal traversal sequences. So the idea of a universal traversal sequence is to not have an algorithm at all, but to just have a list that you read. Imagine taking a graph and labeling each, let's say, a degree D graph, and labeling each exit from a vertex with a distinct number, 1 through D. Okay, so it's just assigning numbers to the edges leaving each vertex. Okay, given any starting vertex, a sequence of these numbers defines a length k path through the graph, right? You're just following the directions. At step k, take the edge numbered k from the vertex where I currently am. Okay. This sequence is called a traversal sequence for your given graph and your starting vertex if following it from V visits all vertices of G. Sorry, G, V, and the labeling. And it is called a universal traversal sequence if it works for every G, every starting vertex, and all labels. So you get the idea, right? A universal traversal sequence is just a series of numbers such that if you just follow the numbers, then you visit every vertex of your graph, regardless of what the graph is or how it got labeled. Which seems kind of cool, right? There's no algorithm anymore, except for just this list of numbers. Okay? And basically, I mean, the space you need to execute this universal traversal sequence is you just have to know where you are on the list, right? So it's literally the log of the number of steps in the universal traversal sequence. No constant factors. Okay? So, why should we imagine that such a beast exists? Yeah? Good. So you can try a brute force enumeration. Right? Actually is a little trickier than it seems at first glance. Okay. So you can say, here's the sequence that will traverse the graph if I start at vertex V of the graph. Here's the sequence that will traverse it if I start at vertex W. So on and so forth. So I have these n different sequences, each of which involves, some sort of traversal of the entire graph. So it seems like I should just be able to concatenate them, and that gives me a universal traversal sequence for the graph, right? Why not? Yeah? Yeah, you're shooting down your own idea. That's so sad, right? So, right? So if you say I'm going to do the V traversal sequence and then the W traversal sequence, well, there's no guarantee that you're going to end up at W when you start from V. So you have to be a little bit more aggressive in the enumeration to sort of case analysis. Where might I end up, right? But if you think about it, there is some vertex you're going to end up at if you start from V. And so you can kind of recursively put things together in order to get such a sequence. But even if this brute force enumeration does work with a little bit more sophistication, what length of sequence do you end up with? Well, you need one for every graph, for every labeling, for every starting vertex, right? So this is going to give you an exponential length, right? And in fact, the dominant term is you need one of these for each graph, right? And a graph is defined by n choose 2 possible edges that are placed in the graph. So it's not even 2 to the n, it's 2 to the n choose 2 times a whole bunch of other terms, right? Because then there's all the labelings, right, of each of these graphs where you have d edges and, so there's a d factorial, except you do this separately for each vertex, so there's another n. So brute force is going to give you a rather scarily large length for this universal traversal sequence, right? So how might we do better? What's the answer in this class? What's always the answer in this class? Yeah? Try a random sequence. No, we don't control the labels, right? But we can make a random sequence. So if we generate a random sequence for a particular graph, and then follow it, what are we doing? Yeah? We're taking a random walk on the graph, right? And we've just argued that a random walk on the graph covers the graph 2n cubed, or sorry, let me put the number in, 2n cubed expected time. Right? Which implies that the probability that we don't cover in 4n cubed time is at most a half. Yes? Yeah? We don't get to pick those, right? The goal here is to generate a sequence that works for an adversarially provided graph. Right? But what this shows us is that this nice short sequence works for half of the graphs. Right? Sorry, got ahead of my notes again. So if we repeat this k times, then the probability of failure drops to 1 over 2 to the k, right? So we just set k equal to the log of the number of labeled graphs. Which is the log of the number is actually something like, it's certainly smaller than this, nd to the nd power. Okay, that aggregates all the things that I talked about before. So, which is just n times the degree times log of n times the degree. Now, what does it mean to repeat a random sequence this many times? Well, it just means you have a random sequence that's that long, because it doesn't actually matter where you start from. Right? So we end up with a universal traversal sequence. D is at most n, so this is basically n squared of length about n to the 5th log n. So if we generate a random sequence of length n to the 5th or so, then it is probably a universal traversal sequence. Which proves, this is the probabilistic method, proves universal traversal sequences exist of polynomial length, which is a really cool result. Okay. However, this is an existential proof, right? A random sequence probably is one, but we have no good algorithm for testing whether a sequence is a universal traversal sequence because it's too slow to check all possible graphs. Right? In terms of construction, the best constructive results is that somebody has given an explicit universal traversal sequence for cycles. It took a whole paper to just come up with a universal traversal sequence for cycles. And everything else sort of constructively is still open. Okay. This is sort of one example from this general category of sort of graph exploration problems. There are all sorts of variations on it. Another interesting collection of variations involve where you have a certain number of pebbles that you can leave at certain vertices of the graph to tell yourself that you've been there before, and which can also be thought of as extra memory of a certain sort. And so there are all sorts of fun algorithmic problems around graph exploration. But that's all I'm going to say about it. Now, the next application I want to show you is a pretty cool application of Markov chains to bipartite matching in D-regular graphs. And this is due to Shishgoel and Kapralov and Kana from 2010. So pretty recent. As in, you were all alive when they invented this. That's recent. So how many people have seen the bipartite matching problem? Oh, you've all got to take, okay, good. The rest of you should take my advanced algorithms class next year, right? So bipartite matching is you've got a 2n vertex bipartite graph, n on the left, n on the right, and you want to pick edges such that each left-hand and right-hand vertex has exactly one incident edge picked. Okay, so you are pairing up every vertex on the left with exactly one vertex on the right and vice versa. And the currently best known, actually I should be a little careful about this, the best known combinatorial algorithms for this problem is order m root n time or so using what are known as blocking flows. Until recently, I could have just said this is the best known algorithm. There's been some huge progress in max flows that basically find approximate max flows in linear time. And I'm not sure what the ramifications are for bipartite matching because I don't know the exact factor of approximation. But certainly in terms of combinatorial algorithms, m root n remains the best known. Except for what I'm going to show you with respect to deregular bipartite graphs. So this is a graph where every vertex has exactly d neighbors on the other side. And they came up with this lovely algorithm that pulls a Markov chain out of its hat. Suppose, and it's based on an older idea called augmenting paths, right? So it's been proven that if you have a matching that is not maximum, okay, if you've got a collection of edges that are matched, but you don't have vertices that are matched, but you don't have a maximum matching, then there exists what is known as an augmenting path, which is a path that starts at a vertex on the left and then alternates between edges that are not in the matching and edges that are in the matching until it ends up at a vertex on the right. Now, if you have an augmenting path like this, I claim you can increase the size of the matching, right? If you throw away all of the current matching edges and you replace them with the non-matching edges on the augmenting path, that increases the size of the matching by 1, right? So if you do n augmenting paths, you end up with your perfect matching. So what they showed is how to find these augmenting paths insanely fast, okay? The standard augmenting path algorithm takes linear time, order m, and so that leads you to an order mn runtime for bipartite matching, so it's slower than the blocking flow algorithm, right? And I just said it's linear time. How could you possibly find an augmenting path faster than linear time? But it turns out that you can, okay? So the way I'm going to think about this, suppose that you have 2k unmatched vertices. That's k on each side, okay? I'm going to look for an augmenting path. I'm going to direct all of my edges from left to right, okay? That's the usual thing that you do when you're looking for augmenting paths. And I mean, notionally, the matched edges are actually directed in the opposite direction, right, to give you a residual graph where you can add a unit of flow. But now what I'm going to do, this is where it gets weird, I'm going to contract all the matching edges. Okay. So I'm going to draw a big circle around each matched pair. I'm still going to have these directed edges. Sorry, this is getting opaque. Let me start over. How do I want to do this? I know. The matching edges don't actually matter, so I'm not going to draw them. What matters is the edges that I care about for the augmenting path, right? But I'm going to draw these contractions that I'm doing of my matching edges, okay? So now that I've done the contraction of these matched edges, what has happened to my augmenting path? Well, it starts at some vertex, and then it visits a sequence of contracted vertices, and eventually it leaves, right? Also notice that from this contracted vertex, this vertex of the contraction only has incoming edges, right? Because it's on the right side. All of the outgoing edges are on the vertex that forms the left side of the matching. Yes? So what I'm really doing is, following an outgoing edge from the left vertex, right, which takes me to a contracted edge, then following from the next vertex to get to the next contracted edge, and so forth, until I get to some contracted edge that includes a vertex that isn't matched, and now I have my augmenting path, right? That didn't make sense, because this vertex is matched. Yes, so this eventually has to take me to an unmatched vertex, right? So this is the final piece, right, of my augmenting path, is to a non-contracted vertex. Now, the thing to notice about this is that the contracted vertices have in and out degree d minus 1, right? Because this had out degree d, but that included the matching edge. This had in degree d, but that included a matching edge. So what's left is that I have in degree d minus 1 and out degree d minus 1 for these contracted vertices, right? Uncontracted left vertices have in degree 0 and out degree d. And the reverse of that for the right. Okay. So, again, a lot of this has shades of the usual algorithm for bipartite matching. I'm going to add an S and T vertices. Okay. I'm going to put an S over here that I'm going to connect to the left side, and I'm going to put a T over here that I'm going to connect to the right side vertices, which is exactly what you do in the flow reduction for bipartite matching. But I'm going to make D parallel edges from S to every vertex on the left, and I'm going to make D parallel edges to T. This is for the unmatched vertices. For every vertex on the right. Okay. Why did I do this? Well, I've just made the in degree and out degree of every non-contracted vertex equal, right? So D edges to and from left-hand side and right-hand side vertices, respectively. Now all of the uncontracted vertices have equal in and out degrees. So I made the contraction made the contracted vertices have equal in and out degrees. This addition of S and T makes the other vertices have equal in and out degrees, but S and T are unbalanced. But now I'm going to contract S and T. Okay. Right. Now you'll notice that S and T, right? S has D edges to every unmatched vertex on the left, which means that it has dk outgoing edges. T has dk incoming edges. So this contracted vertex has in and out degree equal to dk. So every vertex in this graph has the same in degree and out degree, right? What do you call a graph where every vertex has the same in and out degree? And what's special about it? Yes? It's an Eulerian graph, not a cycle, a tour, right? So if a graph has all in and out degrees equal, that is what is known as an Eulerian graph. And these have been studied for a long time and considered interesting because an Eulerian graph always has an Euler tour. And if you haven't seen that, you should go read about the bridges of Königsberg, which is this cute puzzle that Euler came out with. It's about whether you can traverse every edge of the graph exactly once, right? You can find a tour that goes through all of the edges exactly once without revisiting anything. Okay, so that's an interesting property of Eulerian graphs, utterly irrelevant to what we're going to do. Okay, we are going to look at a different interesting property of Eulerian graphs, which is the stationary distribution. What happens if you take a random walk on an Eulerian graph? Okay. And let's look at the edge Markov chain, not the vertex Markov chain. Yeah? Exactly. The edge Markov chain is doubly stochastic. Right? Because the probability of taking each of these, I have to go back a step. So I need to argue that the total probability entering a particular vertex is 1, right? I know that the total probability leaving a vertex is 1, right? But the point is that if I here have some number r of incoming edges, sorry, why am I suddenly getting hung up on this? Yeah, let me write it out this way. The probability that I end up on vertex VW is just equal to the sum over all edges of the form UV of the probability I'm on UV times the probability that I transition from edge UV to edge VW, but that's 1 over the degree of V, right? But I'm claiming here a uniform distribution, right? So this is just equal to 1 over m times the sum over all edges UV of 1 over the degree of, no, that doesn't, yeah, but the in degree of v is equal to the out degree of v. So this is just 1, and I end up with 1 over m as my uniform distribution. Okay? So because it's an Eulerian graph, I have a uniform distribution over the edges, which means, right, what we know about the hitting time is, the hitting time is twice the total number of edges, right? Is m, the total number of edges, right? That's part of the fundamental theorem of Markov chains. Okay. No, sorry, that's not right. The hitting time is equal to the total degree of all the edges in the graph divided by the degree of E in the graph, right? Because the probability of being, sorry, I should take the break now, but let me finish this argument. So we have a uniform distribution over edges, and from that you can say that we have a certain probability of being on each edge, but from that you can deduce the probability of being on a particular vertex by summing the probabilities of the edges that transition into that vertex, right? So probability of being on a particular vertex is equal to the in degree of that vertex times the 1 over m chance of being on each edge that leads into that vertex, right? So that is that's the stationary probability of being on the vertex is the in degree divided by the total edges. And again, by the fundamental theorem, that means that the return time is just 1 over that. It's the total number of edges divided by the in degree of the vertex we're interested in. So let me now ask you about the time that it takes to return to S. And what that means. So imagine that I start at S and start running a Markov chain on this graph. When I return to S, what has happened? Well, I started at S and I wandered around, right? And I went through some series of contracted vertices. And at some point, I hit an uncontracted vertex. The only way out of that uncontracted vertex is to T, and then I go back to S, right? Because from T, the only place I contracted T to S, so that's the only place I can go back, right? So what did I find by returning to S? Well, I found an augmenting path, right? So if I start at S, a path that returns to S finds an augmenting path. Yes? If we only have one, then we will not have an Eulerian graph. This is correct. In terms of analyzing we could put a single edge and then carefully analyze the resulting Markov chain, but by making it Eulerian, I can just immediately turn to the argument that it's a uniform stationary distribution. Okay, it's just to simplify the accounting. Okay, that means that this quantity, HSS, is the expected time to find an augmenting path. So what is that quantity? It's the degree of S. It's the total degree of S, or the total degree the total number of edges, divided by the degree of S. Right? Now, what is the total number of edges? Well, we had ND edges to start with, because we said the graph had degree D. Right? We then contracted away n minus k of those edges. Right? And then we added S, and from S we directed k edges to, or d edges to each of the unmatched vertices, and there are k of those. So, and we also did the same for t. So we added 2dk edges. Now the degree of S is, as we just said, kd, right? We put d outgoing edges to each of the k unmatched vertices. Yes? So we do the math. So this is at most n plus 2k times d divided by k times d, which is n over k plus 2. So if you have k unmatched vertices, then the time to find an augmenting path is n over k. So, right? Which is sublinear, right? This random walk is going to find an augmenting path without visiting most of the edges of the graph. Okay? So the total time for a matching is just the sum over all k of 2 plus n over k, which is order n log n. So, in fact, this finds the whole matching without looking at most of the edges of the graph. This is an actual sublinear time algorithm. Which is remarkable. And all it required is just randomly walking through the graph. Yes? Yes, no, so that's right, sorry. It's the interesting work is sublinear. In order to actually implement this algorithm, you kind of need to, I think you actually have to look at the graph in order to know where to put things and what to contract and so forth. But nevertheless, right? Beautiful, simple bipartite matching algorithm. Obviously, the limitation is it only works for regular graphs, right? Only regular graphs let you go down to this Eulerian property. That makes it all work. This has been generalized in various ways to give you approximation algorithms for bipartite matching more generally, or perfect matchings in slight generalizations where the degrees are all close to each other but not exactly the same. But like, there's no proof that this idea can't be generalized further to give you a beautiful, simple algorithm for bipartite matching in general. Okay. All right, let's stop there for now, take a break, and we will see what I will do with the last 20 minutes of class. Yes.
I was wondering, 'cause I just filled in the form for like the partner thing, so
All right.
I don't know how quick.
Yeah, I mean, the challenge, I mean, if it comes in late, I'm not going to penalize you, but you'll have less time if it turns out that your project is wrong. So, yes.
Question: current PSAT forces develop an algorithm for like 2-color and 3-colorable graph to break all the triangles.
Mm-hmm.
It doesn't give any runtime requirements on this. Does it allow it to be exponential time?
No, we want polynomial time out of it.
Okay. Can I assume that a semi-definite program can be solved in polynomial time?
Oh, you shouldn't have to do that.
Oh. Whoops, because I might have thought this looked similar to the maximal problem.
Yeah, that is a misdirection. You should use other techniques. You can, yes, sorry, you're totally allowed to assume semi-definite programs are solvable, but you don't actually need that for this problem. There's a much simpler solution. It's funny, that actually hadn't occurred to me as a method, but there's an algorithm that doesn't require the power of an SDP solver. Okay, not a lot of time left, and there's one more topic I wanted to present to you. I think what I'm going to do is give you a sort of an interesting high-level story, and afterwards, if it turns out that enough people want details, I will give a lecture next week on those details for those who are interested. Okay. So the stuff that I have shown you with Markov chains so far is cool, but is not the real main application of Markov chains in algorithms and I think even in computer science more broadly. Instead, the real power of Markov chains is sampling from complex distributions. Okay. So there are lots of applications to sampling from distributions, but where the distribution is very complicated. Okay. So one powerful way that often works for doing this is that you create a Markov chain whose stationary distribution is this desired complex distribution. And then you start in an arbitrarily chosen state. And you run the Markov chain for a while. Okay, and I put a while in quotes. And you hope that you converge to the stationary distribution. Okay. And on the surface, this is just like it's a hope, and it sort of intuitively makes sense, right? Because the whole idea of a Markov chain is that it's memoryless, right? If you think about that word, it means after 1,000,000 steps, how is it going to remember where it started, right? And if it doesn't remember where it started, then it's kind of in the station. Then it seems likely that it's going to end up in the stationary distribution, right? And then take your current vertex as your sample. Okay. And I kept up the reason we can expect this to work is basically here, right? The limiting this is saying that the limiting behavior of the Markov chain is to end up in the stationary distribution. right? But of course, for algorithmic purposes, the question is, like, how long is a while, right? How long do you have to run? And this is captured in the notion of the mixing time of a Markov chain. It is the time for, so let me define this. We can have a stationary distribution pi, and we will also have a current distribution q sub t, right? At every time step, there's a certain distribution on where we are. It's initially all concentrated at one vertex. As we run, it kind of spreads out over all of the other vertices, right? I always have to remember to actually look at my notes. Is it this one? Yeah. So the mixing time, or I have a sub-definition, the relative pointwise distance between these two probability distributions is the maximum over all possible states of the difference in probability between the two states divided by the probability that you're in that state in the stationary distribution. Okay? And the mixing time is the time until the relative pointwise distance is less than some epsilon that you choose. Okay. Now, what does it mean for the relative pointwise distance to be less than epsilon? It means that the probability that Q puts on a particular state is between 1 plus or minus epsilon times the probability that the stationary distribution puts on that state. So if your relative pointwise distance is epsilon, you can say that your current distribution closely approximates the stationary distribution everywhere. Right? And so, for example, if I wanted to compute the expectation of something under the stationary distribution, well, using my current distribution would give me an epsilon approximation to that expectation. Right? And more generally, the probability of any event will be within epsilon of its stationary probability. So the probability under Qt of any event is within 1 plus or minus epsilon of the probability under pi. So this is just formalizing the idea that if my distribution is close to the stationary distribution, I can use it instead for whatever my application is, right? So the question is, what is, or what this focuses us on is designing our Markov chain to have a small mixing time, right? So the general trick in this area is to design a Markov chain with a polynomial mixing time. And if you can do that, that gives you a polynomial time algorithm for generating a sample from whatever your complicated distribution is. Okay? And there are a number of different techniques for analyzing the mixing time of a Markov chain and proving that it is small. Okay? And I don't have time to talk about those techniques today. One of them is kind of algebraic. It looks at the eigenvalues of this transition matrix because you know that if you take powers of a we know that long transitions are represented by powers of the transition matrix. If you take the power of a transition matrix, you're basically taking the powers of its eigenvalues. So if all of the eigenvalues are bounded away, if the stationary distribution has eigenvalue 1, if all the other eigenvalues are bounded away from 1, then they will decay exponentially fast. And once they're gone, you'll be left with just the stationary distribution as your distribution. There are also beautiful ways to demonstrate a rapid mixing using coupling, which avoids all of the algebra and instead does a thought experiment that connects your distribution to the stationary distribution by an experiment instead of by math. Since I only have 5 minutes, I'm going to not devote them to how you show mixing, but instead show you an example of where you use this stuff, which is for estimating the volume of high-dimensional convex bodies. So I'm not going to show you the math of this, and that way I can do it really fast in the time that we have left. Nope, it's not in these notes. There's expanders. No, it must be in these notes. Yeah. So the idea here is that you're in some large number of dimensions, and you have a convex body defined by, e.g., a collection of n half spaces and hyperplanes that define a polytope that you might do linear programming over. And like linear programming is looking for the best vertex of that polytope, but suppose that instead you want to estimate the volume. Okay. This problem is sharply hard. So we're not going to get an exact solution. Okay. But the Markov chain approach gives you a fully polynomial randomized approximation scheme. And at its core, it's based on choosing a random point from the convex body. Okay. If you remember when we did DNF counting, we showed this sort of relationship between sampling and counting, right? And counting is about estimating probabilities, right? So if we go back to the Greeks, they had an algorithm for measuring pi, right? What they did was they threw darts at a unit square and asked how often does the dart land inside the circle, right? And that fraction, that probability of landing in the circle gives you pi, right? So you can imagine generalizing this idea, right? The first imagined generalization is to just move this up to high dimensions. You say, make an n-dimensional cube, and that has my polytope inside of it, and throw darts at the cube and see how often they land inside of the polytope. And this would give me an estimate for the volume of the polytope, right? Now, the problem with that is that in high dimensions, you can have these sort of long, skinny polytopes, right? So the circle is very nice, but what if instead I had a polytope that was shaped like this? Okay. This polytope, this is maybe not too bad in 2 dimensions, but as you go up in more and more dimensions, this polytope can be exponentially small compared to the cube that contains it. So throwing darts at the cube will never hit the polytope, and you'll never get an estimate for the volume of the polytope. Okay? So this, again, goes back to DNF counting. We need to change our sampling distribution so that the polytope becomes more common, right? So that we can choose from it. So the trick that is used is, instead of trying to choose from the whole cube, you consider a nested collection. Instead of cubes, they use spheres. But you essentially draw a bunch of concentric circles. And you try to sample from the part of the polytope that is inside one circle and see how often it is also inside the next smaller circle. Okay, so as you're shrinking, right, as you consider these nested circles, you're getting rid of pieces of the polytope, so you're making its overall volume smaller and smaller, right? But eventually you're going to get a circle that is entirely within the polytope. And so at each step, you basically try to compute the volume of the intersection of one of these circles with the polytope as a fraction of the volume of the circle, the next larger circle intersected with the polytope. Okay. And you make the relative ratios of these circles something like 1 minus 1 over n, or 1 over d, which guarantees that you only lose, you sort of lose a 1 minus 1 over d factor in each dimension, and so overall you are still going to have a constant fraction ratio between the amount of the polytope that's in the inner circle versus the amount of the polytope that's in the outer circle. Okay? So that means that instead of trying to, so that solves the problem of the rare event, okay, but because it ensures that the thing you're trying to measure is a large fraction of the thing you're sampling from. But it makes the sampling problem much harder. Instead of sampling from a cube, you now need to sample from this weird shape, which is the intersection of your polytope with a sphere. Okay. So the key is to generate a random sample from your polytope intersected with some sphere. Okay? And you then use that random sample to say what fraction of the next spheres, of the intersections, of the next intersection's volume is, what fraction of the total is the next sphere's volume, right? And you can imagine now multiplying all of those fractions together in order to understand the ratio between the total volume of the polytope and the volume of this little enclosing sphere, of this little sphere that's inside the polytope, okay? So again, I don't want to give too many, I'm not going to take time to give too many details, but essentially I'm showing you how you transform the volume estimation problem into a sampling problem, which is to sample from this convex shape, okay? Now, assuming you believe that, how do you sample from a convex body? Well, there's a pretty natural random walk on a geometric object, which is the geometric random walk, right? So, geometric random walk is you impose a fine grid in the polytope, and then you start somewhere and you repeatedly take a step in a random direction of the grid. So the two-dimensional version would just be that you randomly walk around in Manhattan, right? You go north, south, east, west with equal probability, and pretty quickly you're going to end up in a random spot in Manhattan. Yes? No, no, no. That's the point. You reflect at the boundaries. Right? You don't walk into the Hudson River. You just choose a different direction. You could also just say that those transitions are not part of the Markov chain. Right? You choose a feasible direction for your move. Okay. And the grid spacing is 1 over polynomial in the size of the body, or the width of the body. Again, lots of technical details there. But what that means is that if you go in a straight line, it's going to take you polynomial time to get from one end of the body to the other. Right? If you make the grid spacing smaller than that, you can't possibly have rapid mixing because it'll just take too long for it to be possible for you to be at the other part of the convex body. Okay? So you set this grid size, you take this random walk, and there's a theorem that this mixes in polynomial time on convex bodies. This is based on some deep ideas from geometry called isoparametric inequalities. And it relies on the fact that that all of these bodies are convex, right? So if you imagine a shape like a bow tie, it's kind of like the lollipop graph. It's going to take a random walk an incredible amount of time to get through from one side of the bow tie to the other. But convexity is exactly what prevents bow ties. So again, very high level picture. You take this very natural random walk. It mixes rapidly in convex bodies, which lets you do this estimation of these nested convex body volumes, which you then multiply together to get the actual volume of the convex body. Okay? So I picked volume because showing it in detail requires deep technical stuff that I don't want to cover. But if we do a lecture next week, I will show you in more detail 2 other interesting counting problems. One is counting the number of permanent